Okay, so welcome back. We're on page 312 talking about this example of a function. So here's basically the way this thing is written out in symbolic formation, where, my first state, I'm trying to find an A. I change it to an X, and then and then go to B and change it to a Y and go to, so this is how this thing kind of works. It's, Anyway, the idea is this symbolic notation. Again, I'm not asking you to do that, but this is the symbolic notation for doing what we just described. Now, I've got a really better one to show you, and this thing is called a Turing machine simulator. I kind of like this guy because it really explains what's going on. Okay, so in this particular case, what we're trying to determine is if a binary representation is a palindrome. Remember, it's the same forward as it is backwards. Okay, that's the task. Is this a palindrome? Yes or no? And so what you do is the head is going to start here. It's going to check this one. It's going to go over and check that on that end. And then it's going to just drop them off, so to speak. And then check this one against that one. And then that one against that one. And okay, so let's just look at this for a minute. First of all, if you get down to the bottom, it talks about, here's all the rules. So each line should contain a form of the current state, the current symbol, the new symbol, and the direction we want to go. So for example, let's start at the very beginning here. So here we are at the current state is 0. The current symbol is 0. An underscore means that you can use almost any character or the symbol to represent a blank space. Okay, so basically skip over blanks, and then the new direction, which means like reverse. Okay, so I'm just going to step through this guy. There's a run here. No, it goes relatively fast, so just kind of watch. So it goes doot, 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 doot. Okay, and it ends up with a smiley face, which means it was. Okay, all right, one more. I'm going to do that again. All right, so maybe I'll just do it one step at a time. So here we are, and I go, great. I need to go to the next step. It says go to 1i. That's what I did. And then I'll take anything. And then I keep going. Okay, I finally got to the end like I'm supposed to. And then it says, wait. Now I can change that to a space. And then back up. And then back up. And then back up. And then back up. I'm going to change that one to a space. And then okay, now I can change that one to a space. Now I can change that one to a space. Now I can change that one to a space, and then I'm done. And then I'm going to put out a smiley face to show that it worked. All right, let me just go over here to the data, and let's throw in something that's not a palindrome. So I'm going to change this to like that. Okay, so now it's not a palindrome. So let's run that. Ding, and I got a frowny face. Okay, so this is a pretty decent way of describing how these things work. Again, I'm not going to ask you to write a program for a Turing machine. That's not the point here. Now, so let's get into a little bit about, okay, you told us what's not the point, so what is the point? Okay, fair question, believe it or not. Okay, so there was a thesis that came up, the Church Turing thesis, that basically says that each instruction in a modern CPU can be done as a Turing machine. That's a thesis, okay? So they're not suggesting that you do this, okay? They're not suggesting that you create a central processing unit using a Turing machine. That's not what they're saying. What they're saying is that the Turing machine is good enough that it can emulate any type of instruction that you want it to do. So, in theory, a Turing machine can do anything that a computer program can do. That's what the theorem says. The thesis, the hypothesis is, the answer to this question is yes. Okay? But it'd be very hard to prove. Okay, so now we're going to start talking about something in the world of testing and hypotheses, because we have to cover this, because I cover this sometime in a statistics course, and that's this term called falsifiable. If somebody makes a claim that says, well, I never lie, how difficult is it going to be to prove that that is true? Well, it's dang difficult to prove that it's true. But is it easy to prove that it's false? Well, yeah, all you have to do is just catch them lying once, right? You see what I'm after? So falsifiable, if a hypothesis is falsifiable, okay, which means you can prove it not to be true, okay? Now, what happens if you have a thesis that is not falsifiable? Well, then typically you don't have a very good, not thesis, you have a hypothesis. Typically, if you have a hypothesis that can't be proven correct and can't be proven incorrect, well, then you don't really have a very good hypothesis. Okay, just saying. Okay, so one of the ways out of one of these hypotheses is you could say, well, when we get a more powerful computer coming up, maybe there's a more powerful automaton that's better than a Turing machine, so we just haven't found one yet, so it's bound to be true. I mean, that's pretty wimpy exercise, isn't it? It's like, it's most likely true, and maybe someday in the future we may have something that's better, but right now we don't. Okay? All right. So here's a goofy phrase, and let this kind of sink in a minute. So if you have not been able to falsify the thesis, so A, there is no falsifiable, and nothing better has shown up yet, well then it might as well be true. Now, it doesn't say that it is true, okay? One more time. I can't prove it wrong, and up to now I haven't been able to prove it right, but maybe in the future I could, okay? So it's just as good as being true. I know, that's a fuzzy thing, and your brain is going to have to be that. So it can't be proven, but it's okay that it can't be proven. It's not falsifiable, and one day it might be proven, but right now everything we've done, okay, seems to indicate that it's true. Okay. So this Church-Turing thesis basically said that all computer problems can be done with a Turing machine. Now, what's the significance of this? Well, the Turing machine is considered like the standard for how to determine whether or not something is a computer. Like, I don't know, I've got a calculator or something, and it says, is this thing a computer? You know, what's the legal definition of what a computer is? And so one of the ways you can test to say if something is or isn't a computer is say, is it Turing complete? Okay, let me just stop where we're at and pop on over to this article. So it talks about Microsoft is producing a new programming language for Microsoft Excel. And then they talk about how they've added enough stuff to it so that it is now Turing complete. And it, just like I said here, being Turing complete is a litmus test for a full-fledged programming language, marking the ability to imitate a Turing machine. According to one definition, a programming language is Turing complete when you can implement any possible algorithm. So this thing called Lambda is the new function programming language that Microsoft is producing, and they wrote an article that basically said it's Turing complete. Now do you understand what this thing is all about? It's a mental exercise to begin with, but then you turn right around and use it to say, this process is a computer, or this is a computer language, because it's Turing complete. Okay. So, let's continue. On page 317, they talk about variations, because people have been gnawing at this problem for quite some time, trying to figure out, well, I know how to make this thing better. And so they made some different variations. One of them is two-way infinite tape. Instead of having a tape fixed on one end and have it infinite on the other, they have it infinite in both directions. Okay, somebody tried that. And then multiple tapes. You know, like the 8-track tape where you had tape that had multiple tracks to it, okay? So you could have multiple things going on. A two-dimensional tape, you know, basically like a scorecard where the read-write head can move left and right or up and down, okay? And then a non-deterministic where one choice have more than one choice per combination of state and symbol. Okay, now, bottom line is, after all this tinkering and all these people with PhDs coming up with these really cool ideas on how to make a Turing machine better, when everything is said and done, The answer is no. They didn't actually make it any better. That yes, it may have been maybe a little bit better in one particular scenario, but the original Turing machine is probably good enough. Now, to make the Turing machine do more things, there's a thing called a universal Turing machine on page 327, which typically kind of sort of looks like that Raspberry Pi cluster thing we did before. Remember? I don't know if you remember this guy, but this guy, Raspberry Pi cluster, where you had one machine that was kind of like the controller, and then all the rest of the machines acted as compute pieces. Like, this is the controller and all the rest of these guys. Well, that's essentially how a universal Turing machine works. So I have multiple Turing machines to organize and run the process. So one of them starts with the thing that controls the rest of the guys. Okay, so one Turing machine controls the other Turing machines. So a universal Turing machine can run transitions for another TN. In other words, I can set up a transition and then have it, move to another node, I guess you'd call it. Just like a modern programming language, because modern programming language is I could have, a process over here and then I transfer it over here and it runs, and have it transfer over here and it runs, right? That's how modern programming works. Okay, so it has like 5 parts. It's got states, symbols, and left and right movements like we had before. And then it has the states could be, starting state, accepting state, and unknown number of others. So it's really, this is one of those crazy stories. It's finite but unknown. In other words, there is only going to be so many of them. I just can't tell you in advance how many there are going to be. In other words, it's not infinite. It's finite but unknown. The symbols, you typically start with a blank symbol, the little diamond guy. And then you have an unknown number of other symbols. So once again, it's finite but unknown. And then you have transitions. Okay. So the number of Turing machines. So can we find the smallest number to handle a scenario? In other words, if you give me this thing, can I tell you what is the smallest number of the fewest number of Turing machines would require to be able to produce this thing? And the answer basically is no. Yes, I can find the smallest number that it would take, but I won't be able. I can't tell you what the optimum number is or what the largest numbers would be. Okay, so the way this thing works, it has 3 separate tapes to store. The current state, the original TM, and then the stored new TM. So basically, what's happening is one of the tapes contains the instructions for the other TMs. Okay? So instead of having just all the data in one, this one has data. It just passes its program down to that guy. Program and data. Okay? Cool. So briefly how it works. I scan the third tape, try to match the current state with the first transition. If so, I try to match the first symbol, and then if that's true, I carry out. Otherwise, I move on to the second transition. If no transitions are found, then I stop. Okay, now, so kind of enough of that, and let's get back to what a Turing machine can and can't do. Because again, this is kind of a mental exercise, so bear with me. On page 332, they talk about the limits of a Turing machine. If it's what's called a decidable problem, in other words, you're asking for a yes or a no, like the example for this simulator, is this a palindrome? Yes or no? All I want to know is yes or no. Okay, those are actually pretty good. And then there's one that's called a halting, where it can produce a yes, but it'll loop on a no. Remember we talked about how the 2 different techniques, right? Okay. So that kind of limits what you can and can't do with a Turing machine, just because of those kind of limitations. Okay, I think we're kind of sort of done with Turing machines. Thank goodness. And we're coming up on the 15-minute mark, which is what a coincidence.